Okay. We are recording now, and so we will get cranking. So welcome back, everyone, virtually, and Walt here in person. And going back to the next session. This is a duplicate of Monday's session, by the way, on conducted emissions. So I went through the theoretical portion last week. That's how I'm structuring these, is going through the theoretical portion of things first, and then we come into the lab and show you the practical aspects of how these different test methods work. So if you'd like to, want to go back to review any of the theoretical portions, those recordings are available on the folder that I've made available. I will also point out, I've gotten a few questions from people who are not inside the NASA firewall, and therefore they are not able to access the folders where we are putting these. Gabe, I'm not sure if Gabe Vasquez at Kennedy is on. He was on Monday. He's looking into a public site where he may be able to put those recordings so that the wider audience can view them. I believe it's on the NESC site, which I think is a public site. I'm not sure if that, I don't know that for certain. I don't know if that's behind the NASA firewall or not, but it may be a public site. We're looking at finding some public site where we can put these without getting into too much trouble. Personally, I mean, I get myself into trouble with this kind of thing, but I don't think there's nothing secretive. There's nothing ITAR or anything about what we're doing here. These are all well-published test methods. Mill Standard 461 is a publicly available document. All this test equipment is readily available commercially. So there's nothing that should be secret or restricted or anything like that, in my opinion. So I don't have any problem with sharing this. The whole reason I am doing this is to share this information so that people can benefit from it and be better at their jobs. So we're looking into how we can make these recordings available for the general audience. So we'll let you know once we have that sorted out. So let's see. So getting rolling here. I'm going to do a bit of show and tell before we show any test results here. So I talked at some length last week about LISMs. So let's look at some LISMs. The differential mode conducted emissions is all about, you have to specify a source impedance. And we'll get to the capacitor network that we use for GEVs. But the mill standard defaults to a LISM. But what's in a LISM? All LISMs are not created equal. There are different types of LISMs, so let's look at a couple of them. So this first one I'm going to show you. This is the default LISM specified in mill standard 461G. Manufacturer is Tegum. That's just one manufacturer. This is a 50 amp LISM. It's a 50 microhenry, but it's a 50 amp LISM. We have some other 50 microhenry LISMs that go up to 200 amps, and they have a pretty significant fan on them. And because they're carrying a lot more current, dissipating more power. But this 50 amp one is much easier to just take apart and show you what's inside. Well, look at what's inside. That's a 50 microhenry inductor. So I'll put my hand here so you get a sense of scale. And I just like to show this to emphasize that 50 microhenries is not something you get by accident. You have to mean it. That's a 4-inch diameter piece of PVC, and I haven't counted the turns here, but it's a couple dozen, maybe 3 dozen turns. That's what it takes to get 50 microhenries, which is representing a wire 5 centimeters above structure on on an aircraft or a ship or something, on a military platform, with structure as the return current path. So that kind of configuration has an inductance per unit length of about a microhenry per meter, running for as long as 50 meters. It says that in the appendix of the mill standard, that's where they came up with 50 microhenries as the standard inductance value to use for these Lisons. But you just see that like 50 microhenries is not something you get by accident. There's no stray inductance or parasitic inductance of 50 microhenries. You have to mean it. And that's, of course, the main portion of this Lison. Lisons are generally identified by the inductor value. There are some capacitors and stuff in here, according to the schematic and the mill standard, but the business end of this thing is the inductor. And I mentioned this last week. This is a line impedance simulation network. Sorry, stabilization network. It says it right here on the label. A line impedance stabilization network is the impedances with respect to the chassis, as opposed to a differential impedance, that would be called a line impedance simulation network. And I'm going to show you one of those, show you a couple of those here in just a minute. But a line impedance stabilization network generally will have a measurement port, which is what we have here. There's a 50 ohm termination on it right now. But that's a measurement port here. And you would connect a 50 ohm coaxial connector to that coaxial cable and run to your measurement device, EMI receiver, or spectrum analyzer, maybe even a scope. But the 50 ohm input of your measurement device, it provides the termination for your transmission line, but it also serves another purpose. That provides that high frequency 50 ohm shunt across the 50 microhenry inductor. So if you recall from, and we'll go back and show you the schematic here in just a moment, but you're running your signal, you're running your power lead through the inductor, but then the 50 ohm input impedance of your measurement device will provide that 50 ohm shunt impedance across the inductor at high frequency. So it will asymptote at that 50 ohms. But that's a crucial part of understanding how these Lisons work and how they're meant to be hooked up. If you don't hook anything up to this port, you're not getting that 50 ohm shunt at high frequencies. So you generally are using these in pairs. You would put one of these in series with each power lead, so that the positive and the negative power lead. And when you do that, you're going to generally be taking measurements one at a time. So the one that you're not measuring on, if you're measuring on the positive lead, you would put a 50 ohm termination on the Lison that's on your negative lead. You must do that to get reliable results. Otherwise, your results are going to be goofy, and we don't like goofy results. You end up having to do it all over again, and that takes additional time. So anyway, that's the 50 microhenry Lison. We'll get to that one in just a moment. Walt's holding a custom Lison, but we'll hold that thought and hold the Lison. I'm here all week, Tim, your bartender. Okay, so next I want to show you the 5 microhenry Lisons. And so here we actually have a pair of them, and the sample measurements I'm going to show you are with these. In the interest of time, I'm just going to show you results that I have taken previously, because reconfiguring everything takes a bit of time, and I just figured that wasn't time well spent here. I'm just going to show you the results from these 5 microhenry Lisons that I've taken previously, and then we'll crank into the results with the capacitor network. But this is a 5 microhenry Lison as specified also in Mill Standard 461 in the appendix as an alternate. The label's on the side. Here we go. This is a Stoddard Lison. You can see the label here, 91221. It's also a 50 amp Lison. So you see it looks to be about the same gauge wire for carrying 50 amps. It's a bit smaller because it's 5 microhenries. It's a little bit smaller diameter and shorter. So the 5 microhenry Lison, again with the measurement port over here, where you would connect up to your EMI receiver or put a 50 ohm termination on there. And then it's got a couple capacitors and resistors. But the 5 microhenry inductor is the business end of this thing. And Still trying to get the feel for pointing this camera. But here again, here's my hand. 5 microhenries is also something you don't get by accident. 50 microhenries is very much something you get by accident, but 5 microhenries is still something you have to get on purpose. This is what you have to do to get 5 microhenries. So even when 5 microhenries is suggested as maybe a more realistic impedance, or the 5 microhenry Listen is a more realistic impedance for a spacecraft, yes, that is a true statement that it's more realistic than 50 microhenries, but that doesn't make it terribly realistic. It is still overkill for most of our missions. Okay, so just 5 microhenries is a lot of inductance. Parasitic inductance tends to be on the order of tens of nanohenries, maybe a couple hundred nanohenries if you're talking about a long run of wire. Just for comparison, as I mentioned, 1 microhenry per meter is what you get running a wire 5 centimeters above a ground plane. We generally run a dedicated, with the ground plane as your intentional current path, current return path. We generally run a dedicated return wire with our send wire twisted with it. That configuration has a much lower inductance per unit length, on the order of maybe 100 nanohenries per meter. So even if you run that, if you're running that configuration for 50 meters, then you're getting up maybe kind of toward 5 microhenries total. But 50 microhenries is a pretty big spacecraft. We're generally not dealing with anything that big. So if you got some on the order of 100 nanohenries per meter running maybe 10 meters, then 1 to 2 microhenries is something a little more realistic. So just bearing all that in mind when you pick a Listen, to pick any kind of impedance they use for your conducted emissions or for your whole test campaign, really pay attention to how well that's representing the real impedance that you have on your platform. Because I submit that these types of Listens probably are overkill. And I'll show you the test results that I'm going to show you. Will show how that they can skew your results to be overly optimistic. So we'll come back to that. This Listen, this is a line impedance simulation network. It's upside down here. We can see. Yeah, sorry about that one. I should have told you I was doing that one last, but that's okay. So it's upside down here. This is a space station Listen. Space station has a couple different Listens, I believe, but this is one of them, and this is a line impedance simulation network. I believe. You might help looking out here. Well, yeah, here we go. There's a schematic on the side of this. This is that configuration that I showed last week, where you have the conductor resistance in series with the inductance, and then your overall shunt impedance, your high frequency shunt impedance. And that's basically what we have here. These are 10 microhenry inductors. So we have a pair of 10 microhenry inductors, and they're specifying 25 ohms. Let me put it back down. 25 ohms is the shunt resistance across each inductor. So it's a total high frequency shunt of 50 ohms. And so you see that these resistors are in shunt with the inductor. There are a couple of big capacitors here on the power supply side. So you're feeding your power supply leads in this way, and then your EUT would connect to the other side. So here again, you got to pay attention to the topology. It's not symmetric. Your power supply leads need to go on the side where the capacitors are. If you connect it up in reverse, then your capacitors are shunting out everything before it, and they're not seeing the Listen impedance, and it's defeating the entire purpose. So that's a space station Listen. And I guess one more thought on Listens before I go to the capacitor network. This is the one that Walt was proudly holding. You want to grab this one again, Walt? Sorry.
I was figuring it'd be easier to bring shit over here instead of leaning everything over.
Yeah. But so here's well, actually this is the pace for another space station Listen, but we basically took everything out of this to build up a custom Listen for another program. that program has since been canceled. But so this schematic is not what's in here, but that was what was in here that we removed. This was a custom LISN for a program that was specifying and this is a line impedance simulation network, specifying a pair of 2 microhenry inductors. The program said that they would provide them to us, but not for a while, but in time to test flight hardware, like maybe a year or more from the time we made the request. But we were going to get ready to test engineering models and breadboards. So we said, well, let's try to build one up ourselves. And I had a summer intern 2 years ago that I turned her loose with turned her loose with some help. I gave her a bit of oversight to try to build this up. And she did a great job. And she realized, and I realized, everyone involved with this, we realized it's non-trivial to build a decent LISN that works up to, they were specifying, I believe, up to 100 megahertz. And I mean, in theory, you can calculate based on the diameter of your coil and how many turns and all that sort of stuff. The math for all that is pretty straightforward for low frequencies. And so it's not too hard to get a 2 microhenry inductor to work up to maybe a couple megahertz, maybe up to 10 megahertz or so. But at higher frequencies, well, what do you have? What do you have here? And of course it's successive windings of our coil, but what does the hidden schematic tells you is between these two things? Capacitance. Walt and somebody online get the tie for first prize. Yeah, there's capacitance here. Parasitic capacitance between the windings really wreaks havoc with your ability to get the desired impedance at higher frequencies. And at the end of the summer, when Annabelle had to go back to school, we got this. I don't recall, but I think we got this working up to maybe 30 megahertz or so. And we got it to the point where, okay, if we were going to use this thing to test any hardware, maybe it's good enough for kind of a first try. But you start getting into resonances and stuff like that at those higher frequencies that I would put a big asterisk next to any test results that I got with this thing. Because it could give you some really weird results above 30, 40 megahertz when those resonances kick in. So just the point here is that conceptually, it doesn't seem very hard to build a LISN, but once you actually try to do it and try to measure the impedance up to upwards of 50 megahertz, it's not terribly easy to do. And there aren't really, I don't believe there's anybody making custom LISNs anymore. I did procure one for JWST. I specified it, and the program specified it, but I fed the specs of, the impedance specs to the vendor, and they built us a nice LISN that worked for our system level testing. But it was probably about $10,000. But there was somebody who actually knew what they were doing and could devote the time to doing all the tweaking and the different iterations of this to get it right. So, it's a non-trivial thing to do if you have to build a custom LISN. If it's something you've done before, you know how to do it, and you know what parameters to tweak, that's great. But, I think we can put this down. Thanks, Walt. Walt Leary, he's the only one in the room. So, but anyway, so that's what I'm going to say about LISN. So, anybody have any questions before I shift to the capacitor network? This is really how we do things at Goddard for the most part and per GEVs. Okay, well, I will go ahead and shift gears. I'll point out one thing, meant to show this. This is the clamp that we use to clamp these 5 microhenry LISNs to the table. So I just love that these kind of clamps exist. I had fun clamping these things to the table just because I got to use those honking clamps. But the serious point is that for the LISN to do its job, I mean, your impedance is with respect to the ground plane. So, I mean, as far as the Lizen is concerned, it's just the box itself. It's the metal chassis. Then your metal chassis needs to have a good contact with your ground plane and your test setup. Best way to do that is to really clamp it down to get good metal to metal contact. You don't really want to use copper tape for that. You want to actually clamp it down. So we have these big honking clamps that we use for that. Now the 50 microhenry Lizen, that's a bigger beast. I don't think this clamp's even big enough for that.
Give it a good old college try.
Yeah. Right? We might have some clamps that are even bigger, but it's just another logistical thing when you're using these Lizens. You need some other support equipment like big clamps to use them properly. So moving on to the capacitor network.
See, John, question. This is Mike
Yes, sir.
Garrett. On that 50 microhenry Lizen you just passed, is there a button on there on the upper left? Yeah.
Oh yeah.
What is the function of that?
I don't have my glasses. Let me put my eyes back on.
Measurement port safety switch.
Yeah, measurement port safety switch. So I think it just open circuits things if things kind of go haywire.
Okay. All right. Thanks.
The 5 microhenry Lizens don't have that.
All right.
But yeah, you're
Thank you.
putting these in series with a power feed, so they could be carrying a fair amount of current. So if something is not looking right, that's kind of your abort button.
Gotcha. Thank you.
50 amps.
Yeah. One of those other ones, I think there's actually one of the higher current ones down here. Yeah, right. Yeah, I'll show you that. You don't need to you don't need to bother taking that one out. This one here, I'll just show this real quick. That I believe is a 200 amp 50 microhenry Lizen. Sorry if you can't see this. I wasn't really planning to show this, but this is the fan right here. This is a fan on the side of this thing because that I believe is a 200 amp 50 microhenry Lizen. So yeah, and you're using those kind of Lizens carrying that kind of current. It gets to be a pretty big, unwieldy piece of test equipment that, from everything I'm saying here, is generally not even really appropriate for a lot of the testing we do on spacecraft. So when we're on a spacecraft, we're generally running a dedicated return wire to each individual load. So our inductance per unit length is much lower in a configuration like that. Moreover, we generally run those dedicated wires from the load all the way back to the distribution point, or ideally as close to the battery as we can get it. So the Lizen or any of your impedance networks really should be representing that common source impedance, not the total harness impedance out to your load. So as I mentioned last week, on a military platform where the power distribution is similar to what it would be in a large building, where you're running 60 hertz facility power over a long pair of wires for a particular circuit in one area of the building. That's common source impedance that all those loads are connected to can be quite high. But on a spacecraft, we tend to run a dedicated power feed from each load all the way back to the distribution point near the power source. So that common source impedance tends to be much lower. And so for that reason, we at Goddard anyway, we prefer to, or we simulate that source impedance. We're intending to simulate a battery. And the next best thing to putting a real battery here is to put a lot of capacitance at the distribution point. So the older versions of Mil Standard 461 up to Mil Standard 461C and 462 used a pair of feed-through capacitors, 10 microfarad feed-through capacitors, and they're exactly as described. They just feed the power. They feed the power feed through the capacitor. So you run your send lead into one terminal, and it comes through, and this side goes to your EUT, and then the second capacitor for the negative lead, and the capacitance is from that fed through terminal to the case. So then again, you need to tie the case to your ground plane. Here we tied it to an L bracket, and then we clamp the L bracket to the ground plane. So that capacitance is to the common ground plane, and that is what was specified in the earlier days of the mill standard, but that's at least a starting point toward getting us toward a low source impedance that will simulate a battery. The other part of this, for DC systems only, we put this 10,000 microfarad line-to-line capacitor across here. So it's tied between the positive and negative terminals. And I have a bare one here so you can see it a little better, but it's just a capacitor. It's polarized, so make sure you hook it up correctly. They very clearly mark the positive terminal here, which is also why you wouldn't want to use this on an AC power system, right? So like a 60 hertz facility power, because mill standard 461 applies to that too. It's just when we apply it to spacecraft, we're most of the time dealing with DC power. But if you're dealing with an AC system, you don't want to use this because it's polarized. Bad things will happen if you go the negative part of that 60 hertz cycle. The other part is a 10,000 microfarad cap across 60 hertz is likely to filter that out and compromise your power delivery. So don't do that. But if it's a DC system, we'll put this 10,000 microfarad capacitor across the pair of 10 mics. So you lower that source impedance down to 30 hertz, which is the lower end of the frequency range that we test to. If you do the math, the 1 over j omega c, the 10 microfarad caps are about an ohm at about 20 kilohertz. And the 10,000 mic is about an ohm at about 20 hertz, give or take. So the whole purpose is to look like a battery down to very low frequencies, so that whatever, from a conductive emission standpoint, which we're going to get to here, whatever noise currents your EUT wants to draw, your power source can feed it. Right? You don't want to be limited by the source impedance, and that's one of the major points that I'm going to get across today. So this gives you a low source impedance that can provide whatever current, essentially, that the EUT wants to draw. It also decouples you from your power supply. You can basically use any workhorse power supply. You don't have to specify some ridiculous source impedance for a given configuration. It's essentially the same as putting decoupling capacitors next to your ICs on a PC board, so that the high frequency currents are drawn from these capacitors and not from the supply. So the source impedance that your EUT sees is this, not this. I see there's a question.
Yeah, John. What's the switch on top of the switch box?
Oh, thank you. Yeah, I was going to get to that. That's actually why I showed the bare capacitor. This box is covering it up. This is just a homegrown box that one of our techs in the EMI lab here, Rick Jones, who unfortunately for us, fortunately for him, he retired at the end of December, but he built up this box to put a series resistor and a switch here. So the idea is, okay, you put 10,000 microfarads across the power supply, it's got to draw some amount of current to charge the thing up. So your supply will be current limited until this thing gets up to 30 volts. It's 28 volts. And most supplies do fine with that. This supply does fine with it. But some supplies, I think some of the more modern, like microprocessor controlled supplies, if they go into current limiting, if you don't override the setting, I think some of them will shut down. And so for that kind of situation, putting a 100 ohm resistor, we just picked 100 ohms. There's nothing real magical about that value, but 100 ohms give or take, in series with the capacitor, gives you a smoother charge up rate to put less strain on the power supply while it's trying to charge it up. And then once you get up to the desired, up to 30 volts, then you can switch. You just throw the switch and you're shunting out the 100 ohm resistor. Because once you're up to full voltage, then you don't want that 100 ohm in series with your power feed anymore. So that's what this box is. And then there's a discharge switch kind of on the opposite end of things. When you turn off your EUT, if there's not a sufficient leakage path to discharge, 30 volts from a 10,000 microfarad capacitor, that 30 volts can stay there for a while. And so just hitting this button, I think it's a couple K. Again, nothing real magical about that, about a specific value there, but on the order of a couple K, you hit this button. I'm not going to do it now, but it'll discharge at 30 volts across a couple K in a gentle manner, and then you're back to a safe configuration where you don't have a hot capacitor anymore. So and Rick built this up to mount it directly onto the capacitor, which is very handy. So any other questions about the setup? Because then we'll get into actually or showing you data I have taken, but showing you the rest of the test setup. Any other questions? Okay. So just getting a broader look at our test setup here. So we have our power feed coming through the capacitor network to decouple from the power supply, give us something that looks like a battery, a source impedance at this point that the EUT sees that is very low impedance with these capacitors representing a battery. So what is it we're testing? Well, we have the power leads now run as a twisted pair going to this intentionally unshielded and unfiltered power converter. So this is just an off-the-shelf interpoint power converter. It looks kind of blurry, but it's an interpoint power converter. I can't quite read the part number with my glasses, but it's on a schematic I have in the charts. But it just takes your 28 volts in and gives you plus or minus 15 volts out. Now, it's a switching DC to DC converter. So that means, sorry, there we go. And just the nature of how that works is there's a pulse width modulated control signal that's essentially sampling that 28 volt input, and then it adjusts the pulse width accordingly to control the output voltages within the desired range. You can look on the data sheet. I have the data sheet available, but it's going to give you plus minus 15 volts plus or minus whatever they specify. But it's an inherently noisy process. And to make these things work properly, in a system, you want to very significantly filter the input and the output. Clearly, I haven't done that here. I intentionally wanted a noise-making thing. I always say for EMC engineers, the world is conceptually rather simple because we have two columns. There is one column for noise-making things, a second column for things that may be sensitive to those noise-making things. So this is a noise-making thing. That's exactly what I wanted for these demonstrations. And the power group here at Goddard was kind enough to give or maybe lend me this. I'll have to check with them to see if they want it back. They gave it to me a few years ago and they haven't asked for it back. But anyway, it's come in handy. But it's an inherently noisy process. So show you the waveforms here in just a minute. But these are the output leads carrying the plus minus 15 volts to a pair of load resistors. Power converters don't really like being open circuited. They really need, they like to have a load out there. Some strange things can happen. They can go unstable or what have you. So these are just my load resistors out here. And so now I'll show you the waveforms. Conducted emissions are specified in the frequency domain, but I submit that you really should always look at a signal in the time domain to get an idea of what you're dealing with. Frequency domain is very useful, but it can be kind of misleading. So just getting a look at a signal when you have access to it is very handy so that you at least have some idea of what to expect when you go to the frequency domain. I'll go back over here. So what we're looking at is the input voltage. That's with this high impedance differential probe here. I like to use differential probes whenever I can. Because single-ended probes, the reference is actually tied to the case of the scope, which is tied to facility ground. And that can cause some strange things in your measured results if you're not careful. A lot of times it's just fine, but if you use a differential probe where both leads present a high impedance with respect to facility ground, you generally get more reliable results, and just that whatever your connection to facility ground might be doing to you just is removed from the picture. So another bit of test and measurement stuff that I like to pass along. And then this is just a basic current probe on a scope current probe on the power feed to our power converter. So the two traces we're looking at are voltage and current into the converter. So the yellow trace, the top trace is voltage, and the bottom trace is the current. That voltage trace is centered right around 28 volts. Another little test and measurement tidbit I like to pass along. I'm sorry about this. Just trying to find a stable place here. You've got an AC signal riding on top of a DC level, on top of 28 volts. So a lot of times the tendency is to put that channel in AC coupling mode. And I don't like to do that. AC coupling can fool you. AC coupling can distort the waveform, and it can show you things that aren't really there. If I'm dealing with this type of situation, I prefer to use DC coupling and put a DC offset on it. So I've got a 28 volt DC offset, so that then I can expand, I can expand the vertical scale around that 28 volts, not around 0. So it gives me kind of the same benefit of AC coupling, but it doesn't distort the waveform. So anyway, point is you can kind of see the switching action. Unfortunately, I don't have access to the control signal. It's internal to the power converter. It'll be really interesting to see the rectangular wave that's controlling this. But you can see the effects here. When you're on the on part of the cycle, you're drawing current. The current will go up, and the voltage will go down. The entire raison d'etre of a power converter is to deliver constant power. So a positive delta I should give you a negative delta V. Current goes up, voltage goes down. So that's what happens here. The current's going up, voltage is going down. Then you get to the off part of the waveform, which is quite evident there. And then the current is, because of whatever inductance might be on the input side, current does not like to change instantaneously through an inductor. So the current will kind of keep increasing, but then it'll turn around and come down while the voltage is going up. So you can see that switching action here. And you can also see a lot of high frequency noise riding on top of this sawtooth, particularly on the voltage side. Now, what we're ultimately measuring with conducted emissions here is current, but you can see this significant ringing at each of these transitions. Again, there's no filtering on this. That's the sort of stuff. And remember, this is a test and measurement discussion, not so much a design discussion, but that's the sort of thing to pay attention to, in design considerations, is that ripple is the sort of thing you need to filter out. But as we'll talk about the specifics of differential mode and common mode, those two different types of measurements will help you diagnose which problem you're dealing with, because the solution space is different. So this gives you a look at the time domain, of what this signal looks like. And I guess, so another significant thing is the period. That's about 2.5 microseconds. It's 1 microsecond per division. So from there to there, 2.5 divisions, give or take, so about 2.5 microseconds. So it's right around a 400 kilohertz switching rate, which is right in line with what the spec sheet says. It's 400 kilohertz plus or minus, I don't know, 10 or 20% or something. But we're sitting right around 400 kilohertz. So we would expect, for a periodic signal, it's ugly, but it's periodic with a fundamental of about 400 kilohertz, we should expect to see a harmonic train with a fundamental of 400 kilohertz, and then harmonics of that. Okay, any questions before we shift gears and actually start looking at some frequency domain measurements? Okay, I'm gonna go ahead and put the camera back on the stand. Looked like there might be a question in the chat. Oh, okay, just more of a note. Okay, I'm gonna share the charts now. Okay, so these first several charts are, just an overview of the setup. The first set of measurements that I'm going to show I took with the 5 microhenry Lisens in place. You can see them over here. Can you see the charts? Okay.
Yes.
Okay. Walt answered yes in the room first, and anyway, he's being the smart guy. Okay, so we have our 5 microhenry Lisens here with the big honking clamps, like I showed you earlier, and yeah, power supply going through the Lisens. And here's so we looked at the 5 microhenry Lisen earlier, so your couple capacitors and so on. Okay, so here's a schematic representation of the setup. So it's very simple, 28 volts going through the pair of Lisens into the converter. So, 2815D, there we go. That's the part number of the converter. And then it gives you plus minus 15 volts with respect to the return, and then through a pair of load resistors. So we're first going to do some CE102 measurements, and so I know I've been saying don't use the Lisens, use the capacitor network, but I took these measurements to show you why. All right, I don't like anybody. I was going to say I don't like anybody doing something just because McCloskey said so. I mean, maybe, but by and large, no, seriously. I want to give you the why so you actually understand the rationale for what I'm recommending as opposed to just telling you stuff. All right, so I'm taking these measurements to actually demonstrate the statement that the position that the feed through capacitors are, or the capacitor network is a preferred way of making these measurements. So let's actually go through the measurements here. With CE02, excuse me, CE102 per the mill standard, you're taking a direct voltage measurement off the Lisen through the measurement port. Now our measurement setup specifies a 20 dB attenuator here, just because of the signal levels that are expected, to keep them within the dynamic range of the measurement system. So that's not a prescription. If your system can handle it without the 20 dB attenuator, then by all means don't put it in. But if you're putting a 20 dB attenuator in there, you have to account for that in your measurement system to know that what you're actually getting is 20 dB lower than the real value. And then the side that you're not actively measuring from, you need to have that 50 ohm dummy load on the measurement port. All right, so then here's that look in the time domain. We went through all this. Now I flipped the current and the voltage for this setup in the lab. My apologies here, but so here the current is the top yellow trace, but the current looks a bit different from what we have now through the capacitor network. That's one of the points. We'll see it more dramatically in the frequency domain. The way it looks on the scope looks kind of similar, right? But here you see that the vertical scale is about 10 milliamps per division, and the one that I showed you, it was about 50 milliamps per division. So the peak to peak current is a good factor of 2 or 3 higher with the capacitor network in there. So bear that in mind. that you can see that in the time domain already, and then we'll have a look in the frequency domain. And then again, our 400 kilohertz fundamental switching frequency. So that tells you what we should expect. Well, so lo and behold, we have a very strong fundamental at 407 kilohertz, and then and then the harmonic train. There's some other stuff kind of going on here in between, but we definitely have our strong signature of 400 kilohertz harmonics. And I think I mentioned in my time versus frequency domain session. Sometimes there's a misconception that, well, we shouldn't have even harmonics. Well, that is only true when you're dealing with a perfect square wave with exactly a 50% duty cycle. We're nowhere even close to that. I mean, even if you have a perfect rectangular wave, as soon as you deviate from that 50% duty cycle, you will have even harmonics. So just don't be surprised when you have even harmonics. You will have them most of the time. So this is our send lead. We go to the return lead. Very similar, a little bit different. But the fact that it's a little bit different tells us we probably have significant contributions of differential mode and common mode. If they're exactly the same, then it's likely that it's dominating. One of those modes is dominating. But the fact that they're a little bit different means we probably got a bit of both. So now this is a little bit of a non-standard thing I did, but to prove a point that with the Lizens still in there, I wanted to take measurements of current. Not something we generally do, right? If you're doing CE 102 with the Lizens, you're measuring voltage. But we're ultimately measuring current through the capacitor network. So I want to do a side-by-side comparison of the current with the Lizens versus the capacitor network. So I pointed out yesterday or Monday, I just love the serial number of this probe. It's the 666 probe. I don't think that could possibly have been done on purpose, but the fact that its serial number is 666, we call it the devil's probe here in our lab, but then that's what we do. Anyway, so we look at the current that we measure on the send lead, on the positive lead with the Lizen, and I'll do some comparisons here, so don't worry too much about the specific levels just yet. But so that's the send lead. And then the return lead, very similar, again, a little bit different. So that tells you probably a fair amount of both differential mode and common mode. So first, we're going to look at the apparent impedances. All right, we've measured voltage and we've measured current. So we should be able to calculate what the apparent impedance is at a couple different frequencies. So where I have the peaks labeled here. Now, yeah, and so impedance simply is voltage divided by current, but we're in dB space here. So we subtract in dB space to give the equivalent of division. So we take voltage in dB microvolts, subtract the current in dB microamps, that gives us ohms, or dB ohms, excuse me. So at the fundamental, when we do that, we get 25 dB ohms, and we convert that back to numeric, we get about 17 ohms. And then at the second harmonic, we get about 28 ohms, and up in this high frequency fuzz here, we're getting about 68 ohms. All right, and we do the same thing on the return lead. We get very similar numbers. For the upper two numbers are exactly the same. The fundamental is 16 ohms instead of 17 ohms. So the first order, that's fine. I'm not looking for high precision here. So get good agreement between the two leads. So then we look at the specified Lizen impedance. It's the standard 5 microhenry Lizen, and it's basically 5 microhenries in parallel with the 50 ohms of your measurement device or your terminator you put on there. And so this is the impedance curve they specify. And so the specified impedances are about 12 ohms at 400 kilohertz, just eyeballing this off the graph, about 23 ohms at 800 kilohertz, and then the high frequency asymptote is 50 ohms, so above about 10 megahertz. Now they specify this tolerance of about plus or minus 20%. So with that 20% tolerance, the measured values that we just went through on the last couple charts look pretty good. So certainly good enough for the sake of discussion. So it provides good agreement with the Lisen impedance. So, all right, so far so good. Things, are obeying the laws of physics. I always like it when things actually obey the laws of physics. So now we replace things with the capacitor network, which is what we have set up now. All right. And that's just giving an overall view of the setup. And here's the schematic representation, just has the capacitor network replacing the Lisens now. And now this is pretty much this is the waveform that I showed you earlier that's still on the scope now, just the traces are reversed. But here we go, we're at 50 milliamps per division. Right. So now our peak to peak current is a couple hundred milliamps, where it was about a factor of 3 lower when we had the Lisens in there. So just looking at it, kind of giving it a quick look in the time domain, we can see that there's more current with the capacitor network in there. Or another way to look at it is that the Lisen is limiting the current, which stands to reason you've got a higher impedance in there. It's going to limit the current. So let's look at that a little more in a little more quantitative manner here. So now we'll take our traditional CEO3 measurements, single wire measurements. I know I've been saying we do a true differential mode measurement. That's coming, but I'm doing these measurements to prove a point. So we'll take this measurement on the send lead, take the same measurement on the return lead. There's not really a heck of a lot of difference. Not that we can observe anyway, but then we'll do the side-by-side comparison of the current that we measured with the capacitor network versus what we measured with the 5 microhenry Lisen. Well, at the fundamental, with the capacitor network, we're about 23 dB higher. And at the second harmonic, about 16 dB higher with the capacitors. And in this high frequency fuzz here, around 15 megahertz, we're about 9 dB higher. So the Lisen impedance is limiting your current. There's no question about it. And there's no mystery about it, right? You've got a higher impedance there. It is going to limit the current that you're going to measure. Even if you're measuring a voltage, the equivalent current is going to be lower, as when you relate it through the Lisen impedance. And then the same story when you look at the measurements with the return lead. It's almost the same numbers here. So now we'll do a true differential mode current measurement. So this is what we get here. And so the differential mode low frequency components are about 3 to 4 dB higher than what we get with the single lead measurement. Now remember, going back to the picture, you're putting the true differential mode current is going through the current probe twice. So you got your send current going through here, and then your return current, the true differential mode return current, is coming through the current probe again. So the direct value you're going to measure is going to be twice the true differential mode current. So you have to take that into account. So if it was all truly differential mode current that we were measuring with that single wire measurement, you would expect that this differential mode measurement to be 6 dB higher. Everybody with me? Very central point here. Everybody with me there?
Yeah.
Okay. I hope that's a yes. Is anybody still there? All right. Hey, thank you. So if we're higher than 6 dB, then we're probably something's goofy with our measurement setup. So this is all part of my whole test and measurement philosophy is you should at least have some rough idea of what to expect, because if it's beyond what you expect, then you need to really scrutinize your measurement setup. If we're getting like 10 or 20 dB higher here, that can't happen. There's something that you're not doing right in your measurement setup. But if we're 3 or 4 dB higher than a single lead measurement, that means, okay, we definitely have a strong differential mode component, but that's not all it is. Then there must be some common mode there as well. So when we go to common mode measurements, which we'll do here shortly, we should expect to see a fair amount of common mode as well. Now, when we look at this high frequency fuzz here, the stuff around 15 megahertz, the true differential mode measurement shows those levels about 16 dB lower than the single lead measurement. So we still have a fair amount of a differential mode here. It's above the limit, but that tells us that we should have a very strong common mode component as well. All right, just all different ways of just really scrutinizing these results and making some sense out of what you're seeing. Otherwise, it's just a bunch of lines on a graph. So, summary of differential mode. Traditional single-ended common mode measurements capture both. I'm sorry, not common mode. Traditional single-ended conducted emissions measurements capture both common mode and differential mode currents. You're making two measurements, one on each lead, and it provides you no information about the nature of your potential problem, whether it's common mode or differential mode. If you make the measurements directly, make differential mode and common mode measurements directly, that tells you directly what kind of problem you're dealing with and gets you much closer to diagnosing and solving the problem. That's also two measurements, so it's no additional time over the single-ended measurements, and I would argue probably less time, because if you go into if you have an exceedance and you need to start troubleshooting, you're going to be making these measurements anyway. So just do them from the get-go. Differential mode applies to primary power interfaces only. And the differential mode measurements provide a direct assessment of the contribution to the ripple on the power bus. That's the specific issue you're trying to address. Common mode is a different beast. So you need to understand whether you're dealing with a common mode problem or a differential mode problem, because it points you to, the solution spaces are different. So when you're performing CE102 voltage measurements with a LISN, the LISN impedance can limit noise currents. They will limit noise currents by as much as 10 or 20 dB. And the real point is they can give you artificially optimistic results. So this is why I really do not recommend doing CE102 with a LISN. Unless you have done your homework and know that it is a representative impedance for your platform. If that 5 microhenry LISN is a much higher impedance than anything you're realistically going to see, it will give you optimistic results, and that's the worst possible outcome for a test, as far as I'm concerned. If I get skewed results, I will always take a false failure over a false pass, because a false failure forces me to look at something. And if it turns out to be an exaggeration of the measurement setup, then I have to deal with that and come to some resolution of it. A false pass, oh, la-di-da, I'm good. And then something bites me in the ass at system level. And I don't like getting bitten in the ass at system level, and my management doesn't either. So, all right, so current measurements across the capacitor network provide worst case assessment that is largely independent of the power bus source impedance. So it is worst case, right? But I'd rather have a worst case. So that low impedance will basically give me as much current as the unit under test wants to draw. And I may be doing this before I actually even know that power bus source impedance. So then I can take my worst case current measurements, apply them to that power bus source impedance, and get a worst case assessment of the ripple. So, and then the limit, when we talked about the limit last week, that limit decreases with frequency due to the bus impedance increasing with frequency. And then this is kind of is follow on to the discussion last week about recommend doing upfront homework to define an apportioned differential mode conducted emissions limit, so that the limit is more meaningful and useful, and will be much less stringent than the default limit and minimize unnecessary waivers. So, okay, that is what I have for differential mode. This is a good place to pause. Does anybody have any questions or concerns before we shift gears and go to common mode? Okay. I think this is a good time to go back to the camera to show you some stuff. Can everyone see the lab now?
Yes.
Okay. Pardon me while I take a ritual sip. This is a pretty good thermal mug, but the coffee has been sitting here for an hour, so it is pretty cold now, but hey. That's part of the job. Anyway, okay, so take a look at common mode now. We're gonna look in the time domain first. Again, can't emphasize that enough. Looking in the time domain is a really good thing to do when you can. It's not always practical if you're dealing with signals that are maybe not fully accessible, but when you can, looking at signals in the time domain can provide you a lot of insight that you might miss if all you're looking at is the frequency domain. So I always recommend looking in the time domain first when at all possible. So you know, in the time domain, that means an oscilloscope by and large. And this current probe here, this is, you know, pretty standard current probe used with a scope. Well, it's got a very small aperture. It's meant to basically look at one wire at a time, or maybe you might have a small group of small wires. We've done that. But this is about the largest wire you can fit through that aperture. So to look at common mode, even just on this pair of wires, can't use this probe. But if you do have a probe meant to use with an oscilloscope like this one that has a larger aperture, this is sometimes called a gun type probe. We're gonna get it above that white background there. It's a roughly a 1-inch aperture. So these are really good probes to use on full cable bundles. When you want to clamp around a full cable bundle to get a common mode measurement in the time domain, if you've got a probe like this, this is great. Now the hitch is this one is out of cal, and when I did actually hook this up when I was checking out the setup, and it was giving me some results that weren't really agreeing with these other probes that I'm gonna show you. So rather than show you goofy results from a probe that I know is out of cal, I'm not gonna bother with that. But if you have a probe like this that works and that's in cal, that should be your go-to probe when you're looking in the time domain. So I wish this thing was calibrated and worked properly, but there we go. Now, but all is not lost. When you use these other types of current probe, more of a standard type current probe that we typically use in the frequency domain, you can still do that, but you want to pay attention to whether it has a flat frequency response in the frequency range of interest. This probe here, this is a Pearson 3525. I don't want to sound like I'm doing commercials or anything, but Pearson just makes really good current probes. And a lot of them, like this one included, were made to measure things like lightning strikes, and specifically in the frequency domain. So, I'm sorry, in the time domain. So you hook this thing up to a scope and measure like what kind of current are you picking up from a lightning strike or you know, events like that. And so if you're using a current probe like this in the time domain, you want to make sure it's got a flat frequency response over the frequency range of interest. This probe has a specified transfer impedance of 100 milliohms into a 1 megohm load. And then, I mean, it's half that into a 50 ohm load, but I like to use it into a 1 megohm load of a scope, so that because then the math is very easy, right? Then it's 100 milliohms, it's 100 millivolts per amp, or the other way to look at it, it's 10 amps per volt. Now we're going to be looking at millivolts here, or milliamps, so it's like 10 milliamps per millivolt. Okay, so when you're in the range, and the frequency range of operation is 10 hertz to 10 megahertz. Okay, this probe, this is one of my workhorse probes. I love this probe. It's a Fisher F33-33-2, F-33-2, and now I had the curve up on Monday, but it has a flat response from a couple of 100 kilohertz up to 250 megahertz. So it's a bit of a higher frequency range than this one. I like to when I'm measuring something in the time domain, I like to use both of these probes at the same time and compare what I see on the scope to determine what, if the low frequency content is being skewed with this probe, then it's lower frequency stuff that this one is probably going to help me better with. If the high frequency content is, if it's above 10 megahertz and this thing is kind of giving out, and I see a lot more high frequency ripple that I'm seeing more accurately with this one, then all right, I can remove this one and then look at everything with this one. So just things to think about when you're making measurements. Again, always just be aware of your test equipment's capabilities. You go beyond your test equipment's capabilities, you get nonsense, and that doesn't help anything. So looking at with both of these current probes, and then we'll turn those channels on. Oh, and well, I did not get this one set up properly. But okay. All right, so it's a little bit fuzzy here, but the red trace is the Pearson probe, the lower frequency one, and the green trace is the Fisher probe, the higher frequency one. So we're seeing something comparable. We're seeing something fairly similar. We'll go with that. Now the horizontal scale is 5 millivolts per division for the Pearson probe. So remember, it's 10 times 10 amps per volt. So that's actually 50 milliamps per division. Okay. And then the Fisher probe is 50 millivolts per division. And so in its flat part of the curve, it has a transfer impedance of 1 ohm. So it's 1 volt per amp. So that's also 50 milliamps per division. So again, just knowledge of these things, you can set up the scales so that you're getting an equivalent current scale on each probe. So we see that it's comparable, right? But there's a little peak here that's a bit higher with the Fisher probe that the Pearson probe doesn't seem to be picking up quite as well. So if I had to pick one of these probes to use going forward, I'd probably use the Fisher one because that's clearly higher frequency ringing there. There are plenty of cases where it's lower frequency content is more what we're looking at. And then I ditched the Fisher probe and just used the Pearson probe, but there we go. So just another little test and measurement thing to pass along. So these are our switching, are the edges of our switching waveform here. And so, we see the ringing on the single wire going into the power converter. So we see a lot of common mode ringing lining up with those edges, kind of like what we would expect. But again, just taking a look at it so you know what you're dealing with. I kind of submit that the time domain gives us our closest representation of reality, if you will. It's all an abstraction, right? It's a machine that's interpreting what the probe is seeing. But looking at what you see on the scope here, I believe is kind of the closest representation of what the signal is really doing in real time, literally, because it's the time domain. Looking at it in the frequency domain is also very useful, but it's kind of another layer of abstraction away from what the signal is really doing. So I just submit that you need both. The frequency domain is great, but sometimes just looking at the signal in the time domain can give you that aha moment a lot more quickly than the frequency domain. Especially if like a coupling or crosstalk problem might be much more of a time domain problem, right? Like you got a digital system and you've got all this kind of junk going on, but it's away from clock edges, you never see it. But if one of those, in fact, an issue I was helping with recently, just a couple weeks ago, we had this kind of stuff walking across a serial data transmission. And every now and then, this kind of junk was landing on a clock edge, and was at least we believe was causing spurious clock transitions, but only very occasionally, right? It was a very intermittent problem, but that really helped us explain probably most likely what we were seeing. But anyway, I just point out it's all part of my rant. I fully admit, I'll call it a rant, that we get requirements happy, and sometimes we just sort of lose track of, of real engineering, and just stepping back from the requirements a little bit and really think what is needed from an engineering standpoint here. If the frequency domain information is not getting you where you need to be, hook stuff up to a scope, and that might give you some additional insight. Okay, bit of a tangent, but I just wanted to pass that along. So now we're looking at common mode. These two probes here they're just hooked up to the scope. So these are not part of what we're going to use for our common mode measurements. Again, I'm going to show measurements that we've already taken. In our lab here, I'll just point out the measurement receiver and all of the computer with all our software is in the next room over. Maybe in another session we'll show you that stuff, like maybe the test and measurement session, that maybe we'll go in there and actually show you some of that stuff. But I just made a judgment call. I'm showing you my hand. I made a judgment call that going back and forth between these two rooms would just be very time consuming and probably not really well spent. So that's why I just figured I would show you the results that I've already taken. Anyway, the real probe that we're going to use for common mode measurements in the frequency domain is this one. This is a solar probe. And same problem as Monday. The part number is kind of smeared off. I think it's a 9123. I think I can barely make that out here. Sorry. This probe goes up to 200 megahertz, which is why we measure common mode up to 200 megahertz. This white electrometrics probe, I believe, only goes up to 50 megahertz. That's the extent of what we do differential mode measurements for. So, okay. Any questions before we go and actually look at some results? Okay, then. Okay. Can everyone see the charts now?
Yeah.
Okay. Go to slideshow. Okay, so this is some pictures. What we've been doing here. There's the schematic. Okay. All right, so we looked on the time domain. So all right, so here again, I mean, the time domain signals are, they're still all that ringing is still they're still working on a 400 kilohertz fundamental frequency, right? So we would still expect to see a harmonic train of a 400 kilohertz fundamental. So that's exactly what we see. Now our limit line is different here. So the limit line is 50 dB microamps, a constant level all the way out to 200 megahertz. So I should point out, I guess meant to say this earlier. I'm not going through any measurements of CE 101, the lower frequency range. The measurement techniques are exactly the same between CE 101 and CE 03. It's just the different current probe for the different frequency ranges. Because our switching frequency is at 400 kilohertz, and the CE 101 only measures up to 150 kilohertz. Well, we basically see nothing down there. So I'm focusing on where we actually have some content that's worth looking at. But if I had thought about it, I would have taken a few plots and actually shown that we're just looking at noise floor. But if you've got some lower frequency stuff going on, then by all means, you should definitely look at CE 101. But the general principles still hold. It's just a different current probe to look at the lower frequency range. But it's essentially the same test method. So the first measurement we're taking here is with the current probe right at the capacitor network, or as close as we can reasonably get it. So we have this profile here, and so we'll make some comparisons here as we go along. Then I move the current probe to the middle of the cable. Remember when we talked last week that you're dealing with a mismatched transmission line here. That it's a cable you can treat it as a single wire from a common mode standpoint. You're basically modeling it as a composite conductor above a ground plane. So it's a wire above ground transmission line. It will have a characteristic impedance, 5 centimeters above the ground plane on the order of 300 ohms, give or take. But you're not terminating it in 300 ohms. You're terminating it at least on the capacitor side with, well, at higher frequencies, that's basically going to be a dead short. Like I said, those will look like about an ohm at around 20 kilohertz. So in this whole frequency range of interest, well, and then mainly for common mode, you're dealing with these capacitors. You're looking at a dead short effectively at these frequencies. Okay, so it's a mismatched transmission line, which means you are going to get standing waves, and so the level that you measure, at least when at frequencies where the cable is a significant fraction of a wavelength, is not going to be constant along the length. That's really the central point. When we talk about a cable being electrically long or electrically short, it's always with respect to a wavelength. And the significance of that is that if it's electrically short, if it's a very small fraction of a wavelength, you can treat it as a lumped element, which basically means that looking at how the current or voltage is wiggling in time, the entire cable is moving as a unit. Okay. But when you're at frequencies where the cable is electrically long, and depends on what school of thought you come from, but a general rule of thumb is when it's a 1/10 of a wavelength. Some more conservative schools say 20th of a wavelength, or maybe even 100th of a wavelength. But if we go with a 1/10 of a wavelength, it means that the current and voltage distribution will not be constant over the length over the length of the wire. So this is about 1 meter approximately. I think it's a little bit longer, but we'll go with 1 meter. So 1/10 of a wavelength means our wavelength is 10 meters. So 300 divided by 10, that above 30 megahertz is when this thing is going to look electrically long. So that's when we would expect to see transmission lines kick in, and where the measured signal is going to start to be noticeably different along the length of the cable. Right. So going back here, the measurement at the capacitor network, this is our benchmark. Then we move the probe to the middle. Things are not that much different up to about here, but this level has gone down by not a whole lot, but it's gone down by, maybe 3 or 4 dB. And lo and behold, that's right around 30 megahertz. So, it's just physics. And then we go to the EUT end and show you, do it like a cartoon. That's the capacitor end, that's the middle, and then that's at the EUT right at the input of the box. So up to about 30 megahertz, give or take, call it about 20 megahertz, the levels are not very much different depending on the location of the probe. Above about 30 megahertz, the levels noticeably go down as you get further away from that shorted termination. I walked through at least some of the theory last week in my transmission lines session. If you want to watch the video, I go through the theory in rather painstaking detail, but the bottom line is that at a shorted termination, the current maximum is going to be at the short, which actually kind of makes sense, and then just the math backs it up. But when you have a shorted termination, the current max will be at the termination, and then you'll get decreasing values as you move the current probe away from it. So general recommendation there is when you're making common mode measurements, make them at the shorted termination. That will give you your current maximum. So I believe that's the point I'm making here. So at low frequencies, when the cable's electrically short, things don't really change in any measurable way. But the high frequencies maximum is at the capacitor end for an electrically when the cable is electrically long. So looking at comparisons of what we measured on the positive lead only, and then what we measured for differential mode and common mode, well, we see that for this particular example with this noisy power converter, the differential mode dominates at the low frequencies, but there's still, you know, a non-trivial amount of common mode. And then common mode clearly dominates at least at some high frequencies, but there's still some differential mode. But when you make the measurements directly, you know how much of each one you're dealing with. And you need to know that to implement a proper solution. Differential mode filtering is not going to help you with a common mode problem, and vice versa. Okay. Any questions here before we change directions and go on to the absorbing clamp?
On that previous chart, John, it looks like to me the differential mode is still worse than the common mode at the high frequencies.
It's about comparable. You go up here, that's about 50, I think it's about 45 dB microamps up here, and this is right at the limit of 50. So it's kind of about comparable. The point is that when you measure the differential mode and common mode directly, you know how much of each one is a problem. But when you measure each lead individually, you have no idea.
Okay, got it. Thanks.
I mean, in this case, you need both. You know, I mean, a power converter is a very noisy thing, and so I know Omri was on Monday. I gave her a nice, you know, commercial. At least I think I did. That this is a known problem for power designers, and Omri and her group here at Goddard, I share space with them in Building 20, so they're my neighbors over there. They have done a tremendous job over the last several years and many different programs of refining their designs such that I generally don't have to worry about this as a problem on in-house programs anymore. I haven't for many years. They have really done a tremendous job of putting in the necessary filtering and shielding to keep this junk from going out. I mean, you know, this is what the converter is doing. When you use one of these converters, this is what you are dealing with. But if you don't see this, then it means that your power converter designer has recognized this and has dealt with it with a tremendous amount of filtering. And so this tells you need both differential mode and common mode filtering, but it also tells you like how much of each you need in a given frequency range, right? So here for common mode, you're maybe 5-6 dB above the limit. You still need some common mode filtering at low frequencies, but you need a lot more filtering for differential mode at those frequencies. Because here you're, you know, that's 20 dB per mark there. So you're like 50 dB above the limit down here. So this tells you, all right, I can't neglect common mode. I need some common mode filtering, but I need a lot of differential mode filtering. But the power group has done that and has really done a remarkable job. And it's not just filtering, but they tend to put these converters in in their own shielded compartment in any electronics box to make sure that ensure that all these currents have the best chance of getting back to the source where they belong, and minimize how much of this crap gets out and can wreak havoc on the rest of your system. Okay, so the absorbing clamp. Talked a bit about this last week. I think it bears going back to review at least a little bit of the basics of how this thing works. The basic idea here is that I mentioned you have standing waves on a cable. You're dealing with a mismatched transmission line. Something that's got characteristic impedance on the order of 300 ohms, give or take, and it's terminated in a short circuit. And we'll also look at an open termination here in a bit. It's not a matched line, right? So you're going to get a skewed representation of what is actually coming out of the EUT based on the cable configuration. You're going to get this pattern of peaks and valleys. And just going back to transmission line theory, recommend looking at the transmission line video if you really want to plunge into the math. But you're going to get these resonances at multiples of 1/4 and 1/2 a wavelength, and you get this pattern of peaks and valleys that will be dependent on your cable layout. And while it's always ideal to come to EMI testing with flight light cables or even flight cables, ideally, that's not, I mean, people almost never come here with the actual flight cables. So the next best thing is flight representative cables. And the emphasis there is primarily on like cross section, twisting, internal shielding, and particularly shield terminations. Those should all be representative of the same way you're doing those things in the flight cables. Lengths are great. Lengths would be ideal if you actually have the flight lengths, but a lot of times you're building your test cables before you even know what those flight lengths are going to be. And sometimes that's just not practical. Sometimes you need to build your test cables to be a bit different lengths, to accommodate the test configuration, like thermal vac, for example. So it means that this pattern of peaks and valleys is almost certainly going to be different in your test configuration than it will be in flight. And there's not really much you can do about that. And, that's just physics. And so this is one place where being aware of this at least, puts you a step ahead of the game instead of being Hank Hill and going, what in the hell is that? Which you might do anyway. But you could be getting these skewed test results just based on the test configuration. If you're at a peak, okay, you're going to get an exaggerated level of current, but there again, that gives you a worst case that you actually can see and do something about, or at least assess. But if you've got a significant exceedance coming out of your box at a frequency where your cable lay is giving you a null, where it's looking like a high impedance, so it gives you a current null, this can mask a problem. And that's the worst possible result. You can see that, I have nothing there. I'm fine. You could have, you see with these power converter without any filtering, it's got junk going up to pretty high frequencies. You could well be knocking out, or the cable layout just could basically be masking a potential problem, and you're pretty much defeating the purpose of the test. So, see, there's a question.
Yeah, why don't they require you to come with your flight light cable lengths for these tests if it's
Well, it's always a desire, it's always a request, but like I said, sometimes you don't know what they are. When you're starting to build cables for a test configuration, it might be before those flight cable lengths are defined.
it seems to be at that point of the phase, that's like shortly before integration. I would think that the flight light harnesses have already been designed. At least the length, at least the CAD guy knows how long the cable is.
Maybe, but I'm just throwing that out as one example. It's, if you're at that point where the flight length's great, but the point here is, even if they are the right cable lengths, you might be masking something here, right? You may have some significant emissions at these frequencies where you have these nulls that you're not going to see. So, so if you were able to put a matched impedance at the end of your transmission line, that's one option. It's not a very good one for reasons that I'll mention here. That basically, that would basically, if you were to actually pursue that, you would be breaking your shield termination and putting a 300 ohm resistor in series with it, which I am not recommending. Make that very clear. that opens up a whole nother can of worms. I mean, you're breaking a shield termination, right? You don't really want to do that. So the next, I don't know if I'd say the next best thing, but another option is this absorbing clamp, which is a device that's been used in CISPR 16 based testing, which I am less familiar with. But it's a current probe followed by a series of ferrite elements, and it's basically inserting an impedance in line. At the low frequencies, it's more inductive, but as you go up in frequencies, the inserted impedance is more resistive. It's absorbing, right? It's basically providing a damping resistance. It doesn't quite, at least this curve, this is a representative curve. You know, your mileage may vary depending on your manufacturer, but it gets you up to 150, 200 ohms, which just provides some damping of those peaks and valleys in your measured data. So this is kind of the summary shot there, that and it really is most effective above 30 megahertz. It's because that's where the inserted impedance is more resistive, where it's actually absorbing. So it's dampening out these peaks and valleys and giving you more of an average current reading, basically a more representative reading of the inherent emissions that are coming out of the EUT that are less dependent on the specific cable lay. Right. And then this is another way of looking at it where, you know, I have the shorted termination and then I remove that to have an open termination. And so this shows that above 30 megahertz, the measured results are pretty much indistinguishable whether you have an open or a short circuit termination out here. And those are the extremes, right? It's either a short or an open or somewhere in between. So this just is another way of telling you that you're getting a more normalized measurement of that current that doesn't depend on a termination or really anything going on in the rest of the cable. It's basically telling you what is actually coming out of the EUT.
So real quick, on that last chart. So basically, all we really care about is the integration of that. You know, whether it's over, you know, if it's over, it's okay as long as it's under over there and it averages out. That's what you're saying.
I'm not sure I follow your question.
No, I'm just saying is this gives us the average, right? So I guess what you're
Yes.
saying is, you know, if it overshoots and undershoots, we just really care about the average.
Yeah.
Okay.
Now I'll go back to, let's see here. I have another chart. I'd gone through all this last week, so I want to get to some measurements here. But
Yeah, I'm a little slow.
This good grief. This chart shows measurements with a standard current probe. This is theoretical, but when the blue curve here is transmission line theory of when you are making the measurement at the EUT end far away from your termination. Right. So when you move the current probe to be right at the shorted termination, then you'll bring up the nulls and you'll get the red curve here. So you'll bring up the nulls to look up like what they would be into an ideal matched load, but you'll still have the peaks. So if you make the current, use a standard current probe and make it at the termination, which is the feed through capacitors for power leads or at the feed through port for a shielded cable, that will at least take care of the nulls, but you're still going to have the peaks. Now, if you do that and at high frequencies you're still below the limit, then fine, you're done. You know that in the worst case that you're compliant with the limit. But if you have some significant exceedances at the higher frequencies using a standard current probe, you may need to pay attention to, are those for real coming out of the unit, or are they exaggerated by your cable configuration? So at this point, I'm going to show some results, and then we can come back to any of this as needed. So actually, I'm going to go to the camera here because I have an absorbing clamp, that very absorbing clamp, actually right here on the bench. So, can everyone see the camera? see what the camera is seeing. Is everyone
Yes.
there?
Yes.
Okay,
Yeah, we
so,
hear.
all right, so this is the absorbing clamp. It's the same one that's in that photograph, and it has a couple little wheels here to open it up. And so it has a current probe element here, and here's your series of ferrite absorbers. So these are your absorbing elements. And at low frequencies they will be inductive, but then they are more absorptive at above about 30 megahertz. But you can see it's a bigger, less wieldy. At least that's the way I say it. If it's more unwieldy, it means it's less wieldy, right? So it's less wieldy than a standard current probe. So I highly recommend you do these kinds of measurements in your development lab before you ever even come to the EMI lab. Talk to folks in the EMI lab, talk to my group. We'll be happy to bring some current probes and a spectrum analyzer, or probably even use your own scope if you want to look in the time domain. These are clearly easier to use, and be able to get them around basically any cable you might care about. This is a little more cumbersome, obviously. So this is maybe something less handy to use as a diagnostic in your development lab. We could still bring it over, but it's obviously just a little bit bigger and more cumbersome to use. But that's about all I was going to say about that. I just wanted to show it to you while I had it sitting there. But now we can look at some results. Okay. I can share the screen. All right. All right, everyone see the screen?
Yes.
So you can have this thing, and we did have this thing calibrated down to 150 kilohertz, but you can see right here, it really is, it's specified to use above 30 megahertz. So that's where its function as an absorber is most effective. So here are the results that we get with the absorbing clamp. So we'll compare that with the standard current probe at the capacitor end, because that's our worst case. Well, apologize, the scales are a little bit different here, but so I mean the red line is the same. It's 50 dB microamps for both here. At the low end, we're actually getting slightly higher current levels than we got with the standard the standard current probe, about 4 dB higher. I don't really fully understand that, but I'm not spending a lot of time concerned about that at over 4 dB. If it's 10 or 20 dB, then something's very wrong. But the this I believe is the same as this resonance here. That's at about 18 megahertz, and this is, apologize, that's in the middle of the foot. That's about 7 megahertz. It's down by a little more than a factor of 2. I suspect, well, and it's more than a suspicion. When you're dealing with like resonant frequencies and stuff like that, resonances based on cable length and stuff like that. We say wavelength is 300 divided by the frequency in megahertz. Well, that equation really is another way of saying wavelength is the speed of light divided by, or speed of propagation is really the point, divided by the frequency, right? So when you say 300 divided by the frequency in megahertz, you're assuming the speed of light at 3 times 10 to the 8th meters per second. Or if you plunge into this, you know that the speed of light is some 9-digit number that I haven't memorized, but it's very darned close to 3 times 10 to the 8th meters per second. That's generally close enough for what we do. Anyway, when you say 300 divided by the frequency in megahertz, you are assuming the speed of light in error vacuum, which is 1 over the square root of mu epsilon of your material between your conductors. So that's assuming that it's air or vacuum. and turn the camera back on. Or just stop sharing, right? Okay, so can you see what the camera is seeing again?
Yep.
Yes.
So, between the cable and the ground plane, well, this isn't even air or vacuum. This isn't magnetic, so your relative permeability is still 1. Dielectric constant is probably not 1. But I don't think this is really affecting things too much. Maybe a little bit. But the dielectric constant of this stuff, and it's maybe between 1 and 2. But do you think the relative permeability of this is 1? Probably not. It's a magnetic material. So that mu sub r is going to be something greater than 1. So whenever your relative permeability or relative permittivity, which is the dielectric constant, whenever that's something greater than 1, that is going to shift your speed of it's going to decrease your speed of propagation, right? You can't be faster than the speed of light. At least I don't think we figured that one out yet. But it's going to be smaller. It's going to be lower than the speed of light. So that means that 300 number you put in the numerator, that 300 divided by the frequency in megahertz, you can't use that anymore. It's something lower than 300. Again, 300 is representing 3 times 10 to the 8 meters per second. Right? It's 300 megameters per second divided by frequency. That's where that 300 divided by frequency in megahertz comes from. So once you put that absorbing clamp in there, that 300 number is no longer the one to use. I'm not sure what that relative permeability of that stuff is, but I know it's not 1. It's got to be something greater. And so if that resonant frequency, going back to this, that resonant frequency of that high frequency noise was shifting down by roughly a factor of 2, if that's what it is, right? If this peak with the absorbing clamp at 7 megahertz is equivalent to this peak at about 18 megahertz, that shift is roughly a factor of 2, maybe a little more. That would imply that the relative permeability of that material is about 4. That seems a little low. I would expect it to be a little bit higher than that, but whatever. I'm not entirely sure what it is, but we know that it can't be 1. It's a magnetic material. We know that it's got to be something greater than 1. So again, this is the sort of stuff to pay attention to with your measurement equipment. And I think I have another chart a little further back actually that illustrates that point.
What is that material that bar?
It's well, they're ferrite absorbers. So I don't know anything more specific.
No. I'm talking about the thing. It's not the absorber thing. The piece, that little bar that looks plastic.
That's the foam spacer we use to get the 5 centimeter space in. But that's not the focus of the conversation right now.
Yeah.
So, but this chart here is showing. I noted this when I was taking. I probably took these measurements several years ago. But this is showing that when you put the absorbing clamp in there, your pattern of peaks and nulls will shift, and that's because you're putting this inductive or this magnetic material in there. The pattern of peaks and nulls is dependent on, well, it's the length of the cable, but then also whatever that material is between your conductors that's determining your speed of propagation. And whether when you add some dielectric material like the foam, but especially that magnetic material, those ferrites, it's going to shift that pattern of peaks and nulls. But that's something again to pay attention to. That when you see these peaks and nulls, to be aware of, well, what really is my speed of propagation here? If I'm assuming air, or if it really is air or vacuum, then okay, your 300 divided by the frequency in megahertz should give you pretty accurate predictions of where those peaks and valleys occur. But as soon as you put that absorbing clamp in there, the the peaks and valleys shift. Now above about 30 megahertz, the whole point is with the absorbing clamp above about 30 megahertz, those peaks and valleys are dampened out. Which is again why I say if you're going to use the absorbing clamp, I highly recommend you use it only above 30 megahertz. Because you may get some of these results below 30 megahertz that may just add more confusion than you want. And again, when you're making measurements, you want to minimize confusion. You want to like actually converge on understanding what it is you're doing. And so again, just understanding how these different pieces of equipment work and what they're doing, it's crucial to understanding how to interpret the results. Because so the way I always put it is, well, the absorbing clamp is just one example of many, but it's just another tool in your kit. And you should never think of any additional tool you're introduced to as displacing or replacing anything you already have. It's just an additional tool. So I was a big proponent of the absorbing clamp for a while. I still think it's got its purpose. It's got its uses, but I've kind of gone back to default. I default to using the standard current probe for these common mode measurements, because then at least I've got I've got a better handle on how to interpret what I'm seeing. You know, we put the current probe at the far end, so at the feed through capacitors for power leads, or at the feed through panel for a shielded cable going out to your EGSC. I have a better handle on how to interpret those results. And if I see some really strange behavior at high frequencies that may be due to the standing waves, then we can get out the absorbing clamp and get an additional data point to maybe help us understand what's happening. If we're getting a massive peak with the standard current probe that goes away with the absorbing clamp, like maybe that's what's happening here, right? We get slightly lower values with the absorbing clamp, then maybe the cable A was exaggerating things. So, I'm just introducing the absorbing clamp as another tool, but like anything else, you've got to be very careful when you use it. The last thing I'm going to talk about here is we'll move to making some common mode measurements on the secondary power outputs, because with common mode, as I say, with differential mode, that's limited to the primary power feed to any given unit, kind of by definition, right? The concern is ripple that can be applied to the common source impedance that everyone will see. So that really just applies only to the primary power feed. So in this case, what's coming into the power converter on this side, this is your Gazinta. But common mode is something that we're concerned about on all cables. The common mode current is something that can radiate or cause crosstalk to neighboring cables, whatever. So, I mean, any cable is a potential culprit for common mode. So here we'll take some measurements of the common mode on the output. We'll basically just lump these 3 wires together. I'm going to consider this as a cable bundle. That's more meaningful than an individual measurements on each wire anyway. Like in a real configuration, you would probably twist these together anyway. So first, looking in the time domain, again, we'll have our ringing at the edges of the switching waveform. So not too surprisingly, this looks pretty similar to the ringing we have on the input side, with no filtering. So here we'll put the current probe right near the output of our power converter, and we get this profile. And then we'll do the same thing. We know this is about the same length as the cable on the input side, so it's about 1 meter. So we should expect above about 30 megahertz, the cable is going to be electrically long, and then we should start seeing transmission line effects. So we'll move the current probe to the middle. And let's pay attention to what's happening up here. Actually, across the board, all the levels come down a little bit. And then we move the current probe to be right near the load resistors. Everything comes down a bit more. Well, so on the input cable, on the primary power cable to the input side, the current went up as we got further away from the converter. You know, as we got further away from RUT and got closer to the capacitor network, the current, at least at high frequencies, went up. So why is this different? He asked the class. Anybody?
Maybe you have a wire, the loop between your return and your signal.
You were
It's
on
not
the call
twisted.
on Monday, Wayne. You're cheating.
No, I wasn't.
You were there Monday. I heard you. We talked.
Yeah.
I thought you were. Unless it was somebody who sounded like you.
I don't recall. Well,
Let's get back and check the attendance.
It's,
yeah, but yeah, I'm sure if you would twist your 15 and your return, you know, you would minimize your ground loop, and so in fact you would minimize common loop.
no, that's not really what it is. But, well, okay, I'll give you the answer because we're running out of time. And I was actually, when we took this data, sorry, data is plural. I don't know if Bob Scully is on, but data are plural. So when I took these data a couple weeks ago, I was a little surprised by that, but then I thought about it. I was like, oh, okay, that is actually what should happen. In fact, it's physics, right? So the capacitor network, as you know, the previous set of data looking at the input side. Here's your EUT. So the far end of your transmission line is here. So you look at this as a shorted termination at high frequencies. Transmission line theory tells you that your peak current will be at the shorted termination, right? And then as you go further away from the termination and closer to the source, then at high frequencies, that impedance will, the apparent impedance at your measurement point will go up, which means that your measured current will go down. And that's what we saw. That's for a shorted termination. But here, I'm going to go to the camera here. I can hang around for a few minutes past 11 for anybody who wants to hang around. But I should show you this directly. So here's our power converter, our plus and minus 15 leads going out here to the box. Again, this was all deliberately a cruddy setup from a noise standpoint. I wanted a noise making thing, and baby, we got it. But no shielding, no filtering. But most important for this discussion, is there any connection that you can see here between any of this stuff and the ground plane? This is plastic. Again, I'd say by design, but it's really by intentional lack of design. I didn't want any shielding. I wanted like the noisiest setup that I could, just so I knew I'd measure some noise, because that was the main purpose here, is to show how to make the measurements. You know, but this is not metal. This is not conductive. There's no connection between any of this stuff and the ground plane. So remember that our transmission line is the composite thing. In this case, it's all three of these wires with respect to the ground plane. So do we have a shorted termination of our transmission line with respect to the ground plane? Leading the witness.
No.
Of course we don't. It's an open circuit termination. So it's different. It's a different configuration. It's still a transmission line. It's still a mismatched transmission line, but it's essentially the opposite case. It's an open circuit, which means you're going to have a voltage peak at the far end. And that means your current peak should be at the source end. And that's what we see. So I didn't do that on purpose, but I'm kind of glad that I did it that way, because then it illustrates, again, the common, if you remember nothing else from any of these sessions, the common thing that I try to get across is you always have to pay attention. Just got to pay attention to what the setup is telling you, what your measurements are telling you. And if it's telling you something you didn't expect, then, you know, the measurements aren't wrong. It means your expectations are, right? You gotta change your expectation or your mental model of what's going on if the test results aren't agreeing with what you expected. That's that's a test and measurement thing, but you're usually doing tests and measurements to, well, primarily like with these test methods, it's to check off a box, but don't tell anybody I said it that way. You're testing to determine, does your box meet its EMI requirements? And if it meets them all, great, you're done. You move on to thermal vac or vibe or wherever, or integrating onto the spacecraft, whatever it is you're doing. If you do see an exceedance, then at least in principle, you should be going to the next step of diagnosing the problem and fixing it, or determining, is this really a problem or not? But you measure what you measure. Now, the measurement might be exaggerated by the way you did it, and that's when you got to examine, okay, do I trust the measurement? Did I skew it in some way, whatever? But if you're seeing something different from what you expected, more than likely your expectations are not accurate. So I expected that I would see a similar behavior on the secondary here, that as I got closer to the loads, the current would go up. And I saw exactly the opposite. And then, I realized that's not the configuration that we have here. It's going back to the charts here. Can everyone see the high quality CAD drawing here? Anyone still there?
Yeah, we see it.
Yeah. Yeah, that's my high quality CAD program called PowerPoint. Yeah, there's no connection to the ground plane here. I mean, okay, we EMI people, we know there's no such thing as an open circuit. There's capacitance, right? But there's no conductive connection here. So it is, for all practical purposes, a transmission line with an open circuit termination here. So it's going to have different behavior. It's still a mismatched transmission line, but now it's with an open termination instead of a short. So you've got to alter your expectations based on that. What's a little bit additionally interesting, and thought about this a little more since Monday, going back to these results here. It's not just the high frequency levels that go down. Everything goes down. So even down here, even the fundamental second harmonic we got highlighted here. So I'm sorry, this is the primary. Here we go. There we go. All right. So at the EUT end, if we look here, just look at the fundamental here. We got 61 dB microamps at the EUT, 55 dB microamps in the middle. That went down by about 6 dB. And then at the load, 45. It went down by about 10 dB when you move the current probe out near the load. So all across the board, the levels are going down. So it's affecting the low frequencies too. And just thinking about that since Monday, there's a discussion we had on Monday. I don't know if Ed Chung is on the line again, but Ed brought something up that I didn't fully click until I think after we were done. But you have distributed capacitance here, right? If it's truly an open circuit, you shouldn't see any current at all, any common mode current. That's clearly not true. We do observe it. It's whatever capacitance you have between this and your ground plane, but it's distributed capacitance all the way across here. So at the EUT, or at the direct output of the converter, you basically have the most capacitance looking out this way toward the load. There's the most capacitance between this point and the ground plane. So you're going to see, the maximum current dropped across that total capacitance to the ground plane to come back. I want to update these charts to actually show this, because I think it's an interesting point to carry through. But the closer you get to the load, there's less capacitance between your observation point and the ground plane. So there's less capacitance, so there's going to be less total current flowing across it. So that didn't fully click. I was trying to, the explanation that I was trying to give on Monday, I think was not quite there, but I think that's more to the point. So I
So,
wanted-
John,
Yeah.
what I would say about that, because you setup looked like you still had the sponge on those 3 wires leading up to the load box. My thought on this was that you have common mode flowing, both on the 15 and minus 15, and they would typically return through the return because that's the only path. But what you have going on, because you have an impedance on the plus 15, minus 15, and you have the common mode, it's seeing a different impedance going back on the return, which is about, say, twice the impedance. So you have a mode conversion, and I think that's what's going on. The mode conversion from differential to common mode, or common mode to differential, I should say, because of the
Well,
impedance.
what we're
in the
measuring
line.
is common mode.
Huh?
So what the measurements that I was just talking about were common mode. So
Right.
you
Right.
could think of it as mode conversion, but I think that's overcomplicating it. I mean, all we're really, I mean, just think of this as one wire. For common mode, it's just like one wire going out to some stuff here. And as far as common mode is concerned, it's basically just a wire that just ends in an open circuit.
Right.
And
Right. Well,
and it's
well,
an
you-
open
the
circuit
com-
above the ground plane with some distributed capacitance here. It's the capacitance that is allowing any common mode current at all to flow. At DC, there's no current, right? The DC current's not going to flow through capacitance, but as soon as you get up to 400 kilohertz, well, then that capacitance is going to have at least a low enough impedance to allow some of that AC current to flow.
Yeah, but we know what the common mode is. It's the noise generated in this converter. That's
Yes.
generating the common mode, and they're moving in the same direction on the positive, and in the same direction on the negative voltage, and they should intentionally return back on the return, right? And it's doing it.
Yes.
But that common mode current, because it's returning, and it's returning on an impedance that's higher, at least, than on the positive or on the negative. So you have a mode conversion there. I don't see stray capacitor between these lines and the chassis of that converter.
Then
I
what's
don't-
giving you the path for any of that common mode to get back to the source?
It's the return. It's the return, but because
If it's
the
returning
impedance-
on the return, there's no common mode. We're gonna have
Yeah,
to take
yeah,
this up
yeah, but-
privately, Wayne.
Yeah, but what I'm saying is it's the impedance that's causing the problem. Because it's coming out in one impedance and they're returning on a single wire. Probably if you triple the return wire to balance, it's like you don't have a balance, say a balanced transmission line.
This is the model right here. If differential mode current is the current that's going to come back on the wire. Now, the only thing that's different about that configuration is you got plus and minus 15
And the three wires.
with return.
Yeah.
So if it's all differential mode current, if everything is completely, balanced and everything is coming back on the intentional return path, you have no common mode. But it's the common mode is the net current that is not coming back on the intentional return path and is finding some other path back to the source. And if it's finding some other path that is not conductive, if it's not some actual conductor, then it's some other impedance that is most likely capacitive. That is the only other option. So and I know that there is capacitance between these conductors and the ground plane, and I've shown you in other sessions how to calculate that. So when you say there's no capacitance between the conductors and the ground plane, I don't understand that statement at all.
Well, it's because I saw that maybe the test setup has changed then, because I didn't see a way to say, okay, hey, there's a stray capacitance there between the ground plane and the body of the converter.
Well, to ultimately get back to the converter, that the converter is not tied to the chassis because it's not a metal chassis, and that so
Well,
there's got to be some capacitive coupling to get you back to the converter chassis
right,
as
to the
well.
converter chassis, yeah.
We're
So
really
that's
getting way into the weeds here, Wayne. I'm happy to talk to you about this offline, but
Alright.
I think
Okay.
the point here is that when you're making these common mode measurements, you got to pay attention to the configuration. Do you have a shorted termination? Do you have an open termination? And that's going to affect the profile that you measure as you move the current probe along the length of the cable. And just when you're making high frequency common mode measurements, you have to pay attention to the fact that you're dealing with a mismatched transmission line, and that current distribution is going to be a function of the position of the probe. If you know that you're dealing with a shorted termination, then put the current probe near the short. But in this case, I just kind of, for whatever reason, just thought I was dealing with the same kind of configuration, and I clearly wasn't. And I'm glad I made those measurements to show that, okay, if you have a situation where you have something that's floating with respect to structure, which, you know, that's fairly common. We do that sort of thing where we have a load that's floating with respect to the main spacecraft structure. Well, then if it's not got if it doesn't have a good termination, or maybe there's not even really metallic structure nearby, then you're dealing with a situation where you are dealing more with an open termination. And if you try to measure those common mode currents, that's going to look different. It's your current peak is going to be more at your source than at the load. So again, the general message is pay attention to the configuration. Because if you're measuring something different from what you expect, then the configuration probably isn't what you thought it was. So, I think just have a couple summary slides here. You know, we generally don't make RE102 measurements below 200 megahertz. We make these common mode current measurements to give a more direct and efficient way of assessing the risk of crosstalk. That's what our concern is at below 200 megahertz. And for a typical case of a shielded cable with a shield terminated to chassis at both ends, the cables must be considered wire above ground transmission lines with shorted termination at each end. Or in the case we just talked about, it might be an open termination at least at the load end. And the current distribution will exhibit a predictable pattern of peaks and nulls. For a shorted termination, the nulls will be at odd multiples of a quarter wavelength. The peaks will be at multiples of a half wavelength. If it's an open termination, it will basically be the opposite. Yeah, for low impedance termination, so shield terminated to chassis for signal cables, or terminated at the capacitor network for power leads, the maximum current will occur at the termination, the far end from the EUT. So when using a standard current probe, place it at the load end to ensure that the peak current is captured. That's at the feed through plate for shielded cables, capacitor network for power leads. Absorbing clamp is an alternative option for frequencies above 30 megahertz. Again, use with care. Do your homework. It's just an additional tool in your kit should you decide to do it. And then common mode current measurements can and should be performed as an early diagnostic in the hardware development lab well in advance of official EMI testing in the anechoic chamber. They're quick and easy to perform with clamp-on current probes requiring no disconnections, and provide invaluable information to help identify and diagnose potential problems. In gory details, all the theory I've written up in the GEV section listed there. So thank you all for hanging on a little bit longer. Does anybody have any questions before we adjourn?
Thank you.
Oh, I'll show you one more quick thing while I have the camera enabled. One of the last points there of how quick and easy it is to make these measurements. You know, again, these are clamp-on current probes. If you're not familiar with these, just as the name says, or as that term implies, clamp on, right? And open it up. So closer to the scope to the camera here. It just opens up, clamp it around the cable, clamp it shut. Make your measurement. It really is very quick and easy to use these, and I can't recommend it highly enough that you do this early and often. You know, and when we suggest making these common mode measurements and people say, oh, well, you're going to disrupt my flight configuration. No, we won't. We clamp this around a cable, we make our measurement, and away we go. And you unclamp it and move it to every cable in the configuration, at least the ones of concern. And even in the frequency domain, these measurements take a few seconds. I guess if you have one of the older EMI receivers, it might take a couple minutes, but you know, if you have an FFT receiver, it takes a few seconds. And if you're looking at in the time domain, it's very quick. So
Traditional receiver is about a 5-minute scan, where the FFT is with seconds.
there we go. So yeah, depending on the frequency range, as what Rob just said, with a traditional EMI receiver, it might take a few minutes, 5 minutes. FFT is seconds. Now, okay, an FFT machine is a couple $100,000. Not everybody has one of those, but the point is that even if you have a standard EMI receiver or a spectrum analyzer, you can do these measurements in a couple minutes, and they give you invaluable information about what cables in your setup might be the noisy one, and what you might be able to do about it. With that, anybody have any parting questions, comments?
From my perspective, I strongly suggest everybody get an FFT receiver. Even though it costs a lot of money up front, you're going to save so much time for your customers, yourself, and you're going to be allowed to do even more work in the future because of that. So, you know, if you have issues trying to get an FFT, you know, let us know. We probably provide some guidance or some suggestions to get it through management. But if an FFT receiver has changed the labs here at Goddard completely. In our support, we have better troubleshooting capabilities now that we can use persistence mode. We are doing scans that would take 20 minutes 10 years ago for the project. Now we're able to do them in about, a minute. So you start calculating all those scans in an INT test flow at a spacecraft level. You save the project a day's worth of testing, you just saved them $100,000. That's half the cost for the FFT receiver. So you get a couple of projects on center, and you bring it to them like that, you will have a new FFT receiver in your lab because of that. So, and then that pays off for all future projects too. So I love those machines. Best machines we ever bought.
Oh yeah, we bought 2 of them here at Goddard, and each one of them paid for itself in the first test campaign we used it in.
Oh,
And then-
spades. Yeah.
And then we just have it for continued use.
Yeah.
But yeah, we can talk about the FFT receiver in other sessions. But yeah, that was a good commercial for
Yeah.
FFT machines.
And Road and Shorts will
Just-
come to your
just
area
for
and do demonstrations all day long for free.
Just for a little clarification, when you say FFT receiver, because I could take anything and do an FFT on it, whatever. Do you mean an EMI receiver with FFT capability?
Yes,
Or any
Yeah.
scope also have FFT?
they will have
capabilities.
an FFT, but these are real-time FFT receivers that will do a wide range of frequencies pretty much instantaneously.
Agreed.
And so it's a different beast from just like an FFT capability on your scope. So it's you've been over here and we've used them here, Wayne.
Yeah.
they're-
You can use a scope and do FFT aspects, but you really want to get that information for the scan you did. You're like, all right, I'm taking this measurement. All right, now what's the probe characteristics? What's my cable characteristics? I have to then take all that into account for my measurement, where if you have an FFT receiver in your software, all that stuff's calculated. So you're immediately getting your answer. There's no chance for you to mess up a calculation afterwards or anything like that. So to give yourself some false data, you're getting the exact answer as long as you have it programmed correctly. So, and they're really not that hard to use.
Yeah, and they just give tremendous. They broadened our capabilities for actually looking at signals. That's we could do a whole workshop on those.
Can we
So-
give a little shout out to Lee Hill?
Sure. Yeah.
So, do a Google search, FFT receiver Lee Hill. He actually does, it's about 15, maybe 20 minutes long. He's been doing this demonstration for the IEEE EMI symposium for years. And essentially he shows like, your starter for your propane grill and stuff like that. With a traditional receiver, I can hold that little button over and over again, and you're probably not going to capture that signal unless everything just aligns for you. With an FFT receiver, you can push that little button and you'll see all harmonics of that thing over a 60 megahertz window. It's an amazing tool to figure out when you have emissions problems, to figure out where it's actually coming from, because you can look at it from a persistence aspect, which gives you a time domain, frequency domain, but it also lets you know when that signal is actually being transmitted and when it's not being transmitted, sort of like Bluetooth, where it operates at the same frequency, but it's just a different time.
Mhm.
It's transmitting the stuff. So you can capture all those things with an FFT. You cannot do that with a traditional receiver. You would be sitting there all day long hoping that you would capture it, but you'll probably never do it. But he does a great presentation on there. You can find it, and it's only about 20 minutes.
Lee's a colleague and friend of mine through the EMC Society, and I've seen him give that demonstration at the
Yeah.
EMC Symposium. So yeah, if you can find that presentation, I'll see if I can find that and send out a link to it.
Mhm.
Anyway, we're about 20 minutes past time. Anybody have any final questions or comments before we call it good? Okay, well, thank you all, and we'll get the recording and well, the charts are already posted, but we'll get the recording posted as soon as I get access to it. So have a great day. Oh, I'll point out, I will be on travel, at least I am scheduled, planned to be on travel next week. And if that happens, I will not be able to do these next week, but we'll pick up the week after. What I'm planning to pick up on is conducted susceptibility, CS 101.
That should be a good one.
So, okay. Have a great day, everybody, and great rest of the week.